Welcome viewers to the fifth lecture for the online series of lectures for the course of Algebraic Topology 2. This lecture is dedicated to some important results concerning exact homology sequences and their proofs. Okay, so let me get started with the statement of theorem 1. Suppose 1 is given, the following commutative diagram which involves two exact sequences of chain complexes. So in the top row we have a short exact sequence of chain complexes from 0 to calligraphic C to calligraphic D to calligraphic E to the trivial chain complex. So the chain map from the chain complex C to the chain complex D is phi, and the chain map from the chain complex calligraphic D to calligraphic E is psi. This is an exact sequence. And we have another exact sequence from 0 to C prime, from C prime to D prime, from D prime to E prime, and from E prime to the trivial chain complex 0. There is a chain map from C to C prime, which we denote by alpha. There is a chain map from D to D prime, which we denote by beta. And there is a chain map from E to E prime, which we denote by gamma. So this is a commutative diagram where the horizontal sequences, there are two sequences here, like I said before, where the horizontal sequences are exact sequences of chain complexes, and alpha, beta, gamma are chain maps. So if this is the case, then the following diagram commutes as well. So one has this pth homology group of the cell complex of the chain complex C, and from HPC to HPD, and then from HPD to HPE, which is the pth homology group of the chain complex E, and then from HPE to HP minus 1 C, and goes on like that on the right. So the homomorphism, the group homomorphism from HPC to HPD is denoted by phi p star. The group homomorphism from HPD to HP is denoted by psi p star. They are induced group homomorphisms. And there is this homology boundary homomorphism that we constructed in the previous lecture. We denoted by del star at P. Okay, so there is this exact homology sequence on the top. There is another exact homology sequence at the bottom, which is a long exact sequence, of course. HP C prime. This homology sequence that I'm writing now is in the context of the prime chain complexes. And HP D prime to HP E prime, and then HP E prime to HP minus 1 C prime, and goes on to the right like this. Okay, so this group homomorphism from HPC prime to HPD prime is denoted by phi P prime star, and then HP of D prime to HPE prime is denoted by psi P prime star, and the homology boundary homomorphism, which is a map from HPE prime to HP minus 1 C prime, is denoted by del prime star at P. Okay, now the induced group homomorphism from HP of C to HP of C prime is denoted by alpha P star, and the group homomorphism from HP of D to HP of D prime is denoted by beta P star. The group homomorphism from HPE to HPE prime is denoted by gamma P star. And then from HP1 of C to HP1 C prime is denoted by alpha again, which is alpha P minus 1 star. Okay. So it's a commutative diagram. This is what we need to prove. Okay, so this was theorem 1. So I need to prove it. So I need to erase the statement to find room to prove this theorem 1. So here goes the proof. So we know that these chain complexes C, D, and E are pairs, right? C is the pair CP comma del PC, where CP are abelian groups and del PC are boundary homomorphisms. D is the pair DP comma del PD, and similarly E represents the pair EP comma del PE, where EP are abelian groups and del PE are boundary homomorphisms. Okay, so here CP, DP, and EP are abelian groups, and phi, psi, alpha, beta, gamma are all chain maps. All right, so we know what chain complexes and chain maps mean, right, from lecture 4. Okay, so there was the given commutative diagram um, given in the uh, given in theorem 1, in the statement of theorem 1. Um, there were two short exact sequences of chain complexes, and they were talking to each other uh, via three chain maps, alpha, beta, and gamma. Okay, and that commutative diagram yields the following commutative diagram for all p. So that I'm going to draw on the on right hand corner, because I'm not going to erase it. So in order to do that, I have to keep it in a place where um, I can keep it intact. So here is that commutative diagram. 0 to CP. 0 is the trivial group containing the identity element 0 only, and CP is an abelian group. And from CP to DP, so the map that takes CP to DP is the group homomorphism phi p, and from DP to EP, there is a map psi p, okay, which psi p is a member of the chain map psi. Well, the chain map psi is a family of homomorphisms. Each homomorphism is denoted by psi p for a given p. And then from EP to the trivial group again, 0. So this is a short exact sequence of abelian groups. And at the bottom, I have another short exact sequence from 0 to CP prime, and then from CP prime to DP prime, and then from DP prime to EP prime, and then from EP prime to 0, the trivial group. Okay, and the group homomorphism from CP to CP prime is denoted by alpha p. The group homomorphism from DP to DP prime is denoted by beta p, and the group homomorphism from EP to E prime is denoted by gamma p. So this is the commutative diagram. Okay. This is a commutative diagram. It means that the following equalities of group homomorphisms hold. Beta p composed with phi p is equal to phi p prime composed with alpha p. This follows from the commutativity of the, I should say that this is phi p prime and this is psi p prime. Well, this equality follows from the commutativity of this diagram on the left, right? Phi p prime composed with alpha p is equal to beta p composed with phi p, right? And the commutativity of the right-hand square gives us this equality of composition of group homomorphisms. Gamma p composed with psi p is equal to psi p prime composed with beta p. Okay. So gamma p composed with psi p is equal to psi prime p composed with beta p. So this is the commutativity of the right hand square gives us this equality. And this holds for all p. Okay. Now, from the compositional property of induced homomorphisms, so beta p, phi p, gamma p, these are homomorphisms contained in the family of the chain maps that we are discussing. The chain maps are phi, psi, alpha, beta, and gamma. So and we know that, well, we'll discuss it further, in detail later, probably in the second segment, that these chain maps induce homomorphisms at the level of the homology groups. Okay, so and they respect the way the group homomorphisms corresponding to the chain maps are composed. Okay, which means that we have uh, so we first of all, the induced homomorphism of the composite map on the left is equal to the induced homomorphism of the composition of homomorphisms on the right. Okay, and we'll see that under so the structure of the homomorphism inside the parenthesis is respected under this induced homomorphism, meaning that this is equal to beta p star composed with phi p star on the left, and on the right hand side we have phi p prime star composed with alpha p star. Okay, this is our equation number one, and applying the induced homomorphism on the equality of the homomorphisms on the right hand side, we get gamma p composed with psi p star is equal to psi p prime composed with beta p star. And we know that the structure of the composition is respected throughout the process, and this gives us gamma p star composed with psi p star is equal to psi p prime star composed with beta p star, and this is our equation number two. Okay, so 1 and 2 together give us the following commutative diagram. Let me draw it here. So we are getting mapped to HP of C. Okay, it's the p-th homology group of the chain complex C. And from that to the p-th homology group of the chain complex D to HP of E, and goes on to the right. And at the bottom we have HP of C prime, and then HP of C prime to HP of D prime, and then from HP of D prime to HP of E prime. Okay, and at the level of homology we have this induced homomorphism given by alpha p star. So in the level of chain groups, we have we have this map alpha p, which is also a homomorphism, alpha p from CP to CP prime, and we'll see later in detail that chain maps induced homomorphisms at the level of homology groups, and that induced homomorphism in this case is denoted by alpha p star. So similarly, we have beta p star, and we have gamma p star, right? And these maps are phi p star, okay? The induced homomorphism that is induced from phi p, and the induced homomorphism psi p star that gets induced from psi p. And here this is phi prime p star, and this is psi prime p star. Okay, these two squares commute that follow from equation 1 and equation 2. Okay. So these proves the commutativity of the first two squares in the second diagram of the statement of theorem 1. Let me draw that diagram that we have to prove to be commutative. We have to prove that that diagram commutes. So let me draw that diagram. Here is that diagram. The pth homology group of the chain complex C to HPD to HPE to HP minus 1C and goes on to the right, and here on the at the bottom we have HP of C prime, and that gets mapped to HP of D prime, and then from HP of D prime to HP of E prime, and then from HP of E prime to HP minus 1 of C prime, and goes on to the right like that. And there is this induced homomorphism alpha p star. This is beta p star. This is gamma p star. And this is alpha p minus 1 star. Okay, these maps are phi p star, psi p star, and this is the homology boundary homomorphism, which is del star at p. This guy is phi prime p star, then we have psi prime p star, and then we have here del prime star at p. Okay, so we are supposed to prove that this diagram, that the diagram that I just drew, commutes. So we have just saw a while ago that these two squares commute. Okay, which follow from equation 1 and equation 2. Now we have to prove that the last square commutes as well. Okay. Good. So let us do that. So, but before that, we have to recall the construction of boundary homology. Homology boundary. Let me check the exact term. Homology boundary homomorphism. So let us recall the construction of this homology boundary homomorphism from lecture 4. So we need to construct del p, construct del star at p and del prime star at p. Okay. Let us examine the definition of del star at p first, in the light of what we studied in lecture 4. So given this class E, the class of EP in the pth homology group of the chain complex E, choose dp in the abelian group dp such that psi p of dp is equal to ep. Let me draw a diagram so that we understand this construction better. So let me erase this two diagrams for the moment and then draw that diagram. So there is this abelian group CP, and then from CP to DP, and then from DP to EP. Okay, so there is a map that takes EP plus 1 to EP, which is the boundary homomorphism for the chain complex calligraphic E. So we denote that del P plus 1 E. Okay. And then from EP to the next abelian group, it is actually a short exact sequence. So the two ends, at the two ends, we have just two trivial groups. Okay, and at the bottom we have CP minus 1, and that goes to DP minus 1, and then DP minus 1 goes to EP minus 1, and there are these maps. The boundary homomorphism that takes CP to CP minus 1 is del PC. The boundary homomorphism that takes DP to DP minus 1 is del PD, and the map that takes EP to EP minus 1 is delta PE. So this map is phi P, this is psi P, and this map is phi P minus 1, this map is psi P minus 1. Okay, we know that this diagram commutes. Okay, so we take the class of EP belonging to the homology, the pth homology of the chain complex E, and we know that the pth homology of the chain complex E is equal to the kernel of del PE here, quotiented out by its subgroup image of this map, delta P plus 1 E. Okay, and the class of EP belongs to this quotient group HP of E. And since psi P is a surjective map, because the first sequence, the top sequence here is a short exact sequence, and psi P needs to be an epimorphism. And from the fact that psi P is an epimorphism, we will be able to find an element dp in the abelian group big dp such that psi p dp is equal to ep, right? We can always do that since the map psi p is surjective. Okay, so this was one thing. Now del p dp is in dp minus 1, and this element in dp minus 1 lies in kernel of psi p minus 1. Okay, so this map is psi p minus 1 that takes dp minus 1 to ep minus 1. So the kernel of psi p minus 1 is a subgroup of this abelian group dp minus 1, and the point is that this image of dp under this boundary homomorphism del pd in dp minus 1 belongs to the kernel of psi p minus 1. How do we see that? So we have del pd dp acted upon by this map psi p minus 1, and from the commutativity of this diagram we see that this is equal to del p e psi p dp, right? So which means that psi p minus 1 composed with del p d psi p minus 1 composed with del p d is the same as del p e composed with psi p. So it follows from the commutativity of the right hand square, and we know that psi p dp is ep, so this is ep, and we know that EPE belongs to the class of EP belongs to the pth homology group of the chain complex E, which means that uh, this this guy EP belongs to kernel of del PE. So this guy is 0. So let me write it out here. Since EP belongs to kernel of del PE. Right? EP is a P cycle. Okay. Good. Now, from the exactness of the bottom sequence here, it's an short exact sequence of a billion groups, right? And from that it follows that image of phi p minus 1. So at the side dp minus 1, the sequence is exact in particular, and this means that image of phi p minus 1 is the same as kernel of psi p minus 1. And we have just shown that this guy belongs to kernel of psi p minus 1. Therefore, this also belongs to image of phi p minus 1. It means that there exists an element here in cp minus 1, which we denote by cp minus 1, belonging to the group cp minus 1, such that psi p minus 1, sorry, made a mistake, it's phi. So that phi p minus 1, cp minus 1 is equal to this guy, del p d dp. This relation is important. So we started with this small ep in this element in this group, okay, which is a representative of the class, the homology class, pth homology class in the chain complex E, and we ended up here. Okay, now by definition of the boundary of the homology boundary homomorphism del star p, one has del star at p acting on this homology class. EP is equal to the class of cp minus 1, the one that we get here. The element cp minus 1 belongs to this group cp minus 1. Okay, and the class belongs to the homology class of cp minus 1. Actually, I'm not going into the detail that this is actually a cycle. So cp minus 1 can be shown to be a cycle using arguments following figure 3 of lecture 4. So I'm not going into the detail. So this is what we have derived earlier. It's a zigzag process of defining this homology boundary homomorphism. Okay, so this we number by 3. Okay. Equation number 3. Okay, now, okay, I need room. Let me erase this. Okay. Okay, now, so EP is here. The element EP is in this group, EP. And let EP prime equals gamma P EP. Okay, so EP prime is here, right? So EP prime is the image of EP under the map gamma P, under the homomorphism gamma P. This means this will give us gamma P star acting on the class of EP to be equal to the class of gamma P EP, and we know that gamma P EP is equal to E prime. It's equal to the class of EP prime. Okay. So we need to show that this, where is that? Okay, I think I need to draw that diagram again. So there were two exact homology sequences that were connected by exact homology sequences. So the first sequence is HP of C to HP of D, and then from HP of D to HP of E to HP minus 1 of C. And at the bottom we had this another long exact sequence, HP of C prime to HP of D prime to HP of E prime to HP minus 1 of C prime, and there were this group homomorphisms phi p star, then we have psi p star, we have del star at p, which is the homology boundary homomorphism, and here we had phi p prime star, there is psi p prime star, there is del star prime at p, and there are this group homomorphisms alpha p star, there is this beta p star, and there is this gamma p star, and this is alpha p minus 1 star. Okay, so we already proved that this square is a commutative square. We also proved that this square commutes. We have to prove that this square commutes as well. Okay, so so let me write down what we need to prove. We need to show that del star prime at P composed with gamma P star is equal to alpha P minus 1 star composed with delta star at P. Okay, that will prove that the last square commutes. Okay, and we are going to prove it for any any um, any class EP belonging in the P homology group of the chain complex E. Okay, so we gotta prove this. Okay, so but it amounts to proof that, so this will be equivalent to this, del star prime at P and gamma P star EP is just the class of EP prime, and we know from the definition of del star at P, uh, this is the class of CP minus 1, okay, and this is the class of alpha P minus 1, alpha P minus, well, right, so I don't need it, so let me erase. Okay, so this is something that we need to prove. Okay, all right, so if we prove this one, we'll end up proving that the last square commutes as well. Okay, so let's try to do this. Let me erase it. So I need to, so I think I am not going to need this last diagram anymore. Okay. So we need the commutative diagram that we drew in the beginning of the proof. Yes, which is this one. Okay, we are going to need this commutative diagram, and commutativity of the left hand side square yields psi p prime composed with beta p acting on dp is gamma p composed with psi p acting on dp, right? So beta p composed with okay, I think it's not the first one, the right hand square. The right hand square is this square. Okay, so the commutativity of this square gives us psi p prime composed with beta p is gamma p composed with psi p. Okay, so this is equal to gamma p EP and this is equal to EP prime. This is equation number 4. Okay, so 4 tells us that beta P dP is a suitable pullback of EP prime in dP prime. Okay, so we have just seen in equation number 4 that when psi p prime, this map acts on this element here, okay, in this group, then we get this element EP prime in this group. Okay, so it is in this sense we are saying that beta p dP is a pullback of EP prime which lies in this group dP prime. Okay, now since phi prime p minus 1 composed with alpha p minus 1 is equal to beta p minus 1 composed with phi p minus 1. Okay, so this diagram is a commutative diagram for all p. So now we consider p to be equal to p minus 1. So we take the index to be p minus 1 here, and then we consider the left hand square or the first square. So the commutativity of this left hand square gives us phi prime p minus 1 composed with alpha p minus 1 is equal to beta p minus 1 composed with phi p minus 1. And we are acting these group homomorphisms on the element Cp minus 1 here in Cp. In Cp minus 1. So the index is p minus 1. So Cp minus 1. And one has phi prime p minus 1 composed with alpha p minus 1 acting on Cp minus 1 is equal to beta p minus 1. And what is phi p minus 1 acting on Cp minus 1? That's just del p d dp. Okay, we have proved it earlier. Okay, phi p minus 1 Cp minus 1 is del p d dp. Okay, and now consider this this diagram. It's a square. The map from dp to dp prime is beta p. Okay, and the boundary operator acting on dp takes us to dp minus 1, and the boundary operator acting on the abelian group dp prime takes us to d prime p minus 1, and the map dp minus 1, the map that takes dp minus 1 to d prime p minus 1 is beta p minus 1, right? Beta p minus 1. This square commutes. Okay, so the commutativity from this square, we arrive at del p d prime composed with beta p dp. Okay, good. Now, so how does this map works? How does this map work? Phi prime p minus 1 take C prime p minus 1 to D prime p minus 1. Okay. And here we have seen that when the map phi prime p minus 1 act on alpha p minus 1 cp minus 1, we get this element in D prime p minus 1. So this is what I'm writing now. Alpha p minus 1 cp minus 1 is the desired pullback of delta p d prime beta p dp in C prime p minus 1. Okay, because this is an element in C prime p minus 1. When this element is acted upon by phi prime p minus 1, we get del p d prime beta p dp, which is an element here in D prime p minus 1. So it is in this sense the desired pullback of this element in D prime p minus 1 is alpha p minus 1 cp minus 1 in C prime p minus 1. Okay, good. Okay, now let me try to erase the last diagram and draw this diagram. So this will illustrate the fact more clearly. There is this map, there is this abelian group C prime P or CP prime, and that gets mapped to dP prime, and then from dP prime to EP prime, and the map that takes CP prime to dP prime is phi p prime, and the homomorphism that takes dP prime to EP prime is psi p prime. And here the boundary homomorphism that takes Cp prime to Cp minus 1 prime is del P C prime, and the map that the boundary homomorphism that takes dP prime to d p minus 1 prime is del P d prime, and the map that takes E prime P to E prime p minus 1 is the boundary homomorphism del P E prime. Okay, and there are this homomorphisms which are phi p minus 1 prime, and this one is psi p minus 1 prime. Okay. Good. Now here we started with this EP prime, okay, which belongs to EP prime, and then we ended up with the pullback of EP prime here in dP prime, which was beta p dP. Then we took the exterior, so the boundary, when we applied this boundary homomorphism onto this element in dP prime, we obtained an element here in D prime p minus 1, which is precisely del p d prime of beta p dP, right? And then we figured out the pullback of this guy in C prime P minus 1, which is alpha P minus 1 of Cp minus 1. So now, from the definition of homology boundary homomorphism, which is analogous to equation 3, is given by delta star prime at P acting on EP prime here gives us the class of this alpha P minus 1 of Cp minus 1, which is nothing but the homomorphism alpha P minus 1 star acting on the class of Cp minus 1. Okay, this is what we were supposed to prove, and that proves the that the square on the far right in the commutative diagram, in the diagram of the two exact homology sequences, commute. Okay, QED. All right, good. It's time to take a break here. We'll be back with more results in the next segment. Thank you for attending this first segment of the fifth lecture.